Hello, and welcome to the second series of talks as part of the Graduate School of Arts and Sciences Graduate Student Speaker Series, or the GS4. Today, it is my pleasure to introduce Itamar Allali, and we will allow a few minutes at the end for questions. And so, Itamar, I will turn it over to you. Thank you.
All right. Hello, everyone. So my name is Itamar, and I'm a rising third-year graduate student in the Department of Physics and Astronomy. And today I'm going to talk about some work that I did with my advisor, Mark Hertzberg, and it's going to be about quantum decoherence of dark matter. So just right off the bat, that is a lot of jargon. So I promise that I'm going to go through all of it, and please let me know if you have questions. All right, so just an overview of my talk. I'll start by talking about what decoherence is. And so this will involve talking a little bit about quantum mechanics and going through some details of that. And after that, I'll talk about the motivation for this project, which has to do with dark matter, what dark matter is and why this has to do with that. And finally, I'll give some results of our calculation and I'll summarize. So first of all, let's talk about quantum mechanics. So quantum mechanics is originally a theory of physics that was derived in the early 20th century for atomic scale physics. An important note is that it doesn't necessarily only apply to small scale physics. In principle, it should apply to larger scales. And that is sort of something that I'll talk a little bit about with the topic of decoherence, how that is responsible for why we really only apply quantum mechanics on smaller scales typically. But just moving on from that for now, so the probably one of the only two equations you'll see in today's talk, but this one should be here. It's a Schrödinger equation. So this is the governing equation for quantum mechanics. And so it describes this thing right here called the wave function. Oops, excuse me. So that's the wave function, this Greek letter psi. And it's a function that describes the state of a particle in quantum mechanics. So for example, if you were to describe a particle in classical physics, you would talk about its position or its velocity, but in quantum mechanics, you would talk about its wave function. And what the wave function corresponds to is it corresponds to the probabilities of measuring certain outcomes. So for example, you can think of the wave function as a distribution of probabilities, let's say in space. And so the value of the wave function at a certain position gives you the probability for measuring that particle at that position. Now, something that's special about the Schrödinger equation is that it's linear. And what this means for our purposes is that any two wave functions, which are legitimate solutions to the Schrödinger equation, if you add them together, that also gives a legitimate solution to the Schrödinger equation. And so this suggests that a particle can be in two states at once, which is a little bit strange compared to what we're used to thinking in classical physics. So this leads to this idea of Schrödinger's cat, that particles can be in a superposition of multiple states. And so Erwin Schrödinger came up with this thought experiment to actually criticize this idea that something macroscopic like a cat could be in two states at once. So just to go through the details of this experiment, rather thought experiment, the idea is that you have a cat in a box, and inside a box there's some radioactive element that is hooked up to a source of poison, and the decay of the radioactive element, which is governed by quantum mechanics, has some probability to occur, and if it does occur, it triggers the poison which kills the cat, and if it doesn't decay, then it doesn't trigger the poison and the cat stays alive. And as long as you don't know what happened, then quantum mechanics says that the radioactive element and therefore the poison and therefore the cat will evolve into this state of being in both states at once, of the cat being both dead and alive. And you don't really know what happens until you open the box. So this thought experiment was sort of a way of poking fun at why quantum mechanics seem to not make sense, because we aren't used to seeing macroscopic objects in two states at once in a superposition. So I thought it would be good to go through a sort of famous experiment to show some of the features of quantum mechanics and how they relate to what I'll be talking about today. So some people may have learned in school about the double slit experiment. So this is an experiment that it was originally done using light in the 1800s to show that light behaves like a wave. And so what you have here are waves of light, wavefronts of light that go through these two slits. And what happens when the waves pass the slit is that the waves start to spread out. And so you can see there are black circles of waves and red waves. And because the waves spread out, they interfere. And so across from those two slits, instead of seeing two bright spots, you get a pattern of bright and dark spots that look something like this. So in the middle, you have a big bright spot, and then followed by two dark spots, and then slightly less bright spots, and so on and so forth. And this is known as interference. And so it's something that's been well understood in physics, having to do with light waves for a very long time. But as I said, in quantum mechanics, we describe particles in terms of wave functions. So if the particles are described by a wave, then they should exhibit this phenomenon as well. And so that's exactly what happens. So, if you, instead of shoot light waves at these two slits, but you instead aim a beam of particles at the two slits, then the wave function of the particle will spread out through the slits and will result in interference like this. And so what happens is that the particle goes into a superposition, like the cat, of being in two states at once, and being the state of going through the upper slit and the state of going through the lower slit. And so different features of quantum mechanics related to this were verified much earlier and sort of motivated developing quantum mechanics, but actually this exact experiment can be done with particles. And so I have just one example here of an experiment done in 1990 by Gaylor and Zellinger. And they used a beam of neutrons and they shot it at a pair of slits. And here you can see an interference pattern. So the points on the plot are data points of the number of neutrons that were piling up at a certain position. And as you can see, it sort of follows a similar interference pattern. Okay, so I promised I'd talk about decoherence. So what is decoherence? So this phenomenon of things going into a superposition, of being in multiple states at the same time, it's not something we usually see, right? The Schrödinger-Cat seems ludicrous because you don't typically experience things being in multiple states at once. So the reason for this, and the reason that that larger objects like cats and like you and I seem to be oblivious to quantum mechanics, is because anything with many molecules or many particles has a lot to interact with. So it interacts with its environment, and it does this frequently. And as soon as these quantum systems interact with their environment, they no longer have their own individual description, but now you describe, you have to describe the particle and its environment at the same time, because their wave functions, the descriptions of these particles, become intertwined. And so this is known as quantum entanglement. And because the environment is very complex, it becomes very difficult to keep track of the environment. And so this eventually leads to the loss of these quantum properties of interference phenomena, like we saw in the double slit experiment. They tend to disappear once the system interacts with its environment. And so this is the process that's called decoherence. It's the reason that we don't typically see things being in multiple states, or the effects of things being in multiple states like interference, but rather regular classical physics usually applies, and it's because things interact with their environment and this results in decoherence. So we can see the same thing happening in the double slit experiment. So if instead of just letting this beam of, say, neutrons go through undisturbed, we shoot some other particle at it, let's say a photon, to try to detect which slit the neutron went through. So this new additional particle, the photon, goes through, and now it interacts with the neutron that's in a superposition. And so because of the entanglement that the description of these two particles now becomes intertwined, you get that the photon will evolve into a superposition too. It will also have two states at the same time, one having interacted with a slit that went through, or excuse me, a neutron that went through one slit, and then the other interacting with the neutron that went through the other slit. And over time, or over multiple interactions with the photons, which here are playing the role of the environment, the system stops behaving in a quantum way. So what you can see here is that as you have more and more of these photons interacting with this neutron, the interference phenomenon starts to disappear. So starting over here, we have something that looks pretty similar to the interference pattern that we saw before when there was no environment that was messing things up, but it's slightly less pronounced. And then as more and more photons or whatever the environment is interact with our quantum system, the interference starts to disappear. And you get instead just one big bright spot, which you may have expected two bright spots because we had two slits, but in this case, the slits would be very, very close together. So it would look like just one big bright spot. And something I wanted to point out is that this image that I got from this experiment with neutrons looks pretty similar to these images, particularly the one on the left over here. So I thought it's pretty interesting that, you can already sort of see that in that experiment, the interference wasn't perfect, right? There was the neutron system wasn't totally isolated from its environment. And so you have a little bit of decoherence happening there already. So I thought that was an interesting observation. Okay, so moving on to talk a little bit about the motivation for this project and how that relates to dark matter. So first of all, what is dark matter? So dark matter is a mysterious form of matter, and it makes up about 85% of the mass of the universe. So here I have a diagram of our galaxy, the Milky Way, and this right here is a side view of that. And so if you didn't know, the galaxy itself is mostly flat. It's this spiral that's in a flat disk. And that blue circle around everything, this halo, is mostly made of dark matter. So it really does make up most of the mass of the universe, and yet we don't really know too much about it. So it's most likely that dark matter is made out of particles that we haven't discovered yet, that are not in the standard model of particle physics, which includes electrons and protons, but rather some new form of particle. And it hasn't yet directly been observed. All we know about dark matter is its gravitational effect, how it affects the structure of our galaxy and of other structures in the universe. And it's usually assumed that dark matter behaves classically. So what I mean by this is that it doesn't really care about the laws of quantum mechanics, but just really classical physics. And the reason for this is that it's considered to be a very large structure. It's a macroscopic scale of physics. And so those things, as we said, like a cat, we don't typically expect to behave in a quantum-y way. But as I indicated, that has to do with decoherence. So, in principle, dark matter should follow the laws of quantum mechanics. And the question is whether or not decoherence is prominent. And so, one thought might be, well, what if you have this clump of dark matter and it's in a Schrödinger-Cat-like state where it's in two states at the same time? Will that, in fact, decohere very quickly like it does for you or for me or for a cat or for any other macroscopic object? Or does it have a chance to stick around for a while? And so I just want to point out, right, that most matter, the reason that it decoheres very fast is because it's constantly interacting with its environment through electromagnetic interactions and other things. And so the thing that's unique about dark matter is that so far we only know about its gravitational interactions. And gravity is a lot weaker than all the other forces. So because it's such a weak interaction, we might there might be a chance for dark matter to decohere much more slowly. Although it's not clear what the observational consequences would be, having some kind of Schrödinger-Cat state for dark matter exist for a very long time might be something that could be detected. And even if not, it would at least provide a unique example of something that decoheres very slowly, which so far that's not a commonplace thing. Usually decoherence is a very quick process. And so the problem that we're trying to solve, the calculation we're trying to do, is to see if you have this Schrödinger-Cat state for dark matter and it interacts with its environment. So we'll think of a proparticle coming in and interacting with this, this superposition of a clump of dark matter. Then the proparticle has interacted with this, and so it now is entangled with it and also evolves into a superposition of, in this case, interacting with the blue clump or interacting with the red clump. And we want to figure out how quickly this causes decoherence to occur. How quickly does this take the superposition of the dark matter in the Schrödinger-Cat state to lose its quantum behavior? And so these clumps that I'm going to talk about are not going to be bound objects like a planet necessarily, but rather just statistical fluctuations of the density of dark matter in the galaxy. So as I said, the galaxy is full of dark matter, and so we'll just look at these sort of random over-dense regions, and so I'll call them clumps, but they're not really clumps. And the environment is going to be any particles that pass by. So for dark matter in the galaxy, this will be the rest of the matter in the galaxy, which is mostly made of hydrogen, although it could be really anything else that passes by. And for a model of dark matter, I'm going to talk about the axion a little bit. So the axion is a proposed particle that might be the dark matter. It's a very light particle. So you may know that protons are about 1,000 times as heavy as electrons. The axions, at least the favored mass for an axion, is predicted to be about 100 million to 10 billion times lighter than an electron. So it's a very, very light particle, and it has no spin. And that is, it doesn't matter so much what we choose as the model for dark matter, although the results that I'll show you in a minute are based on this model. And so just to get to sort of the punchline of this, so I promised only 2 equations in this talk. So here's the second equation. And so this is an equation for the rate of decoherence. So how quickly the Schrödinger-Cat state of the clump of dark matter loses its quantum behavior. And you don't have to pay too close attention to all the details in this formula, but just sort of to highlight things, it is directly related to the density. So these Greek letter rho are densities of dark matter and the density of the proparticles. And that should be expected because if you have a more dense region of dark matter, then there's more things to interact with. And so this interaction happens faster, and then the decoherence happens faster. It also scales inversely with the mass of the axion. So whatever model you choose for the dark matter, the sorry, there's some music in the background. Okay. Whatever the mass is, if you have a heavier particle for your dark matter, that corresponds to these fluctuations being much smaller. And so the decoherence is again is going to be slower if the particle is heavier. But slightly more easy to digest results. So here's a better visualization of what we found. So I'll draw your attention first to the blue curve. So the blue line is showing the time it takes for this clump of dark matter to decohere, to lose its quantum behavior as a function of the mass of the particle, whatever choice we have, or whatever we choose the mass to be. And I'll highlight this range of masses right here between 10 to the minus 5 and 10 to the minus 3. And these units is electron volts divided by c squared. So like I said, for context, that mass range is between 100 million and 10 billion times lighter than an electron. But the reason I highlight that mass range is because it's favored by other recent work that tests the axion as a good model for dark matter. So this range of masses is what corresponds to the abundance of axions in the universe being the right amount to account for the amount of dark matter that we see. And so as you can see in this plot, the decoherence time can be very long. I mean, for these masses, it runs off the page. The black dotted line is the age of the universe. So at least naively, it seems that you can have, if you have a clump of axions of this favored mass range, then the Schrödinger-Cat states they live in, they'll exist for much longer than the age of the universe. So of course, if it has any observable consequences, we would see it, right? The green curve is if this clump of dark matter were to fly through our atmosphere here on Earth. And so as you may expect, that causes the decoherence to be much faster because the atmosphere is a lot more dense than the rest of the galaxy. There's a lot more particles for the dark matter to interact with. And so the quantum behavior of this clump would disappear much quicker. But still, you get pretty observable time scales for this mass range. However, just one consideration before I conclude is that because we're talking about these clumps, which aren't really clumps, they're just these fluctuations in the density of dark matter, these fluctuations would tend to spread, right? They're just random over dense regions, and they tend to spread out over time. And so if we think about the way they spread out over time, well, for really, really light particles over here, that doesn't change at all the picture, because the decoherence time is so fast that there's no time for the clump to spread. However, for the mass range I highlighted before, the clump has enough time to spread, and so this bends these curves down quite a lot. So we no longer get that the Schrödinger-Cat clump can exist for longer than the age of the universe, but it's still conceivable that it exists for a pretty long time. So about 10 to the 10 seconds, and that's something like 300 years. So not 14 billion years like the age of the universe, but 300 years is a pretty long time. So if these states were to exist, they could survive for a lot longer than any kind of ordinary matter would stay in a quantum state. So it seems to be pretty interesting. Again, for the case of the atmosphere, the decoherence time is much smaller. So as expected, it would be a lot less likely for us to see these quantum looking states if the dark matter were to pass through the atmosphere. That being said, this red curve right here is for it shows you the amount of time it would take for this clump to pass through the galaxy, or excuse me, through the atmosphere of the Earth. So even if the decoherence time isn't very long, if it's if you were to come up with a way to observe the phenomena that would be associated with this state, it would need to be at least longer than that red line, so that the state survives long enough to go through the atmosphere and sort of be detected by the experiments here on Earth. So to summarize, we started out with this idea that dark matter might be unique in that it has the chance to have these Schrödinger-Cat quantum superposition states live for a very long time compared to regular matter. And we found that the clumps of dark matter in the galaxy, again, they're not really clumps, might actually live for a very long time in these superposition states. This ended up being pretty favored in the range of masses that are favored by other work. So that seems to be a nice coincidence. And currently we're working on more work to try to incorporate slightly more subtle effects. So, for example, if the superposition of the clump weren't, two different mass distributions like in the picture, but something that, maybe a superposition of different pressures or something that wouldn't be so easy to distinguish, it's possible that the decoherence would take a lot longer to occur. Thank you for your time, and I'll take any questions.
Thank you, Itamar. There's a question in the chat. Would you like me to read it for you?
Sure.
Okay. Two related questions. Perhaps you said this, but are the clumps themselves pure states? And second question, how do you choose the parameters of the clumps besides mass?
Sure. So are the clumps pure states? So we're treating them as pure states, that they're sort of each distribution, or each of the two states in the superposition, is in itself a pure state. And so then the combination of those two would also be a pure state. I hope that answered the question. Maybe I should look at the chat. So
And then the second question is, how do you
Right.
choose the parameters of the clumps besides mass?
Sorry, I should have just asked it.
Yeah, it's okay. So that's a good question. So the parameters of the clumps are mostly set. So let's see, the density is set by the density of the dark matter uh, in the galaxy or wherever you want to do this calculation. The size of the clumps we set by the de Broglie wavelength of the dark matter. So there's a typical speed for dark matter particles in the galaxy, and so the de Broglie wavelength gives you the length scale for these fluctuations, how big they are on average. So that's what was used. And then if I go back to this, oops, it's not working. Let's see, if I go back to the formula for a second, there's also these parameters, so beta and alpha, which are just used to differentiate between the two clumps. So for example, if you have a superposition of two clumps that are of a slightly different size, then maybe you set the size of them in general by the de Broglie wavelength, but then beta for one of the clumps is 1 and beta for the other clumps is 1.1 or something. And so it's just that they differ by a slight amount, but they still are both around the characteristic size of fluctuation. Does that answer your question?
Yeah, thanks.
Great. Any other questions?
I just had a quick question for you, Itamar. So great talk, but I was just a little confused about the
Thanks.
spreading. Not sure if I quite understood what you meant by that and why it bent the curves the way it did. I might have missed that.
Yeah, no, that's a good question. So remember that the clumps aren't actually bound objects. They're just statistical fluctuations. They're random changes in the distribution. And so those, think of them as like noise. And so they tend to spread out and then disappear, right? So if you think of the distributions around the average density, and then there's just sort of a random peak, over time, the peak tends to disappear. And so the reason that tends to bend the curves down and make the decoherence a little bit faster is because once the clumps sort of spread out, they cover more area, they interact with more of the environment, and so the sort of size of the clump just becomes bigger. So maybe that helps. I mean, another effect that I'm not sure how much stronger this is, but because it's in a superposition of these two different distributions, well, they're going to spread slightly differently. So as they spread, they probably tend to look a little bit different too, and that becomes that also contributes to the quicker decoherence. Does that answer your question?
Yeah, thank you very much. That helps clarify it a bit.
Okay, thanks.
There's a question from David Hammer.
Hi,
Yep.
Itamar.
Hello.
This wasn't covered in Physics 11.
No.
I'm wondering if it, I've never thought a tiny bit. I actually long ago I was doing dark matter research.
Okay.
Yeah, and what, 40 years ago? No, 30 something. Anyway, I never thought about that in the same breath as the topic of decoherence. So it's
Sure.
kind of cool. But this is like decoherence on this giant scale.
Yeah,
And
that's right.
I'm wondering, is anybody thinking about like how general relativity calculations would go with the universe in a superposition of mega mass states? Like it seems as though that's the ongoing work circled. Okay.
That's a really good point. So I think maybe the first half of what you're asking, so we are thinking about how because everything in this project so far has to do with just Newtonian gravity. So we're thinking about incorporating the effects of general relativity because general relativity has a lot more of a fine view on ability to sort of see finer differences in gravitational interactions. As far as it would affect, much larger scale phenomena, I don't know. I mean, I'm we're really looking at this more as like an isolated thing. So I'm not sure if I can really address the second half of your question, or maybe I just didn't understand it. Yeah, I agree that it sort of is. Yeah, so just to give you an idea, right? A typical size for these things, because we've set the size of them by this really has to do with the speed of the motion of these particles in the galaxy, which is something that we know it's measured. So that, the clumps are typically 100 meters or so big, maybe somewhere between 10 and 1,000 meters. So, so we're talking about a football field. Well, yeah, I didn't say it. Yeah, so it's a football field, which exactly.
I see.
Right.
I see. Okay.
But it's a good question.
Yeah. No. If
Any other questions?
it were larger, I'd ask like something around like gravitational lensing or something. But when it's for that makes it like little teeny tiny, nothing sized.
Well,
bit.
and I think.
So,
Right. I think if it were larger, it would be. I mean, it wouldn't have a chance to live for so long, right? It would. The rest of the galaxy or the rest of the universe is going to interact with it so frequently because of.
I guess that's right.
Right.
Yeah.
So we're sort of in this unique regime where it might be possible.
Right. Okay.
Good question. Thanks.
Are there any more questions?
I have one more quick question if I'm not cutting anybody else off.
No, I think, yeah, thanks.
So do you have some reason to think that these cat states would be like preferentially produced in the early universe or something? Or are you just like using them as a proxy for more generally entangled states and trying to get a sense for how long they might last?
Originally the latter. Well, I think in general, just kind of using them as a, hey, if this existed, what would happen, is useful in and of itself. I don't know about necessarily these things being produced in the early universe. So, we've been wanting to think a little bit more about how this state would be produced. But if you can just imagine some dynamical process that might lead to a state like this, it's exactly these states that would survive, right? So for example, if through some interaction, an axion goes into some ludicrous superposition, that decoheres very quickly. If it were in fact a bound state that's in a superposition, a bound state has a gravitational field around it. So, if this was like a planet in two different spots or a planet of two different sizes, everything orbiting it, everything nearby would disappear really quickly. So, as much as I can address how these things would form, I'm not sure, but this sort of idea of a statistical fluctuation, which is invisible from far away and only really, has an interaction when the environment gets very close. That's the thing that would survive. Or maybe you can imagine a process that does launch into a more ludicrous superposition, and so the decoherence happens, but what's left over is sort of this subtle random thing. Not sure that answered your question, but that's
No,
as much
does.
as
Really
I've thought about it so far. Sure.
Yeah.
We have time for one more question. I believe Alec had a question. If you'd like to unmute yourself, Alec.
Right. So, hi, Itamar.
Hello.
I think you actually just started to touch on this. So I was thinking about, so if you're measuring kinematics of planets, galaxies, or clusters, then in this model, the effects you're seeing due to dark matter are due to the superposition of the mass or pressure or whatever states that you're considering, correct?
Yeah, if I understand what you're saying correctly, so just the the dynamics we're talking about are very local. It's just sort of the random stuff nearby, you know, other hydrogen atoms interacting with it, not necessarily thinking about the effects it would have on the structure of the galaxy.
Okay.
Is that what you're asking, or?
Yeah, because I'm just trying to think if we have measurements of, right, the whole reason dark matter is proven to exist is because of, you know, kinematics of bodies within galaxies.
That's right.
But you're you're now attributing those kinematics to a superposition of multiple states.
Yeah. So
as opposed to
right. So the thing that we're sort of imagining is all of those kinematics that are responsible for our understanding of dark matter today are still there. So you still have this, you know, uniform background, or it's not actually uniform. You know, the distribution of dark matter from the center of the galaxy out it's not constant, but whatever that distribution is, that's there as a background, and then this is sort of just a slight perturbation to that somewhere out there. And it's small enough that it doesn't affect the things around it, although, you know, we could consider the back reaction of this state on, you know, the rest of things, but we're sort of approximating that as being so negligible that all we have to really care about is how it interacts with its local environment.
Okay. Right. And because you're considering it local, then it's hard to use data of that sort as basically conditions to constrain the model, I guess.
Yeah, that's right.
Okay. That's what I was thinking. Thank you.
Thanks.
We're just about at time, so thank you so much, Itamar. It was very interesting. If anyone has any questions, I'm sure that you can reach out to him directly. But we are
Please.
recording this session, and we'll share it afterwards. So thank you again for all of you for joining today.
Thanks, everybody.
Thank you.